The required takeoff speed for a certain airplane is 100 meters per second, and the plane starts from rest at one end of a 1 kilometer long runway. Part A, calculate the acceleration necessary for the plane to reach the required takeoff speed. So let's list the kinematics variables that we know. It says the plane starts from rest, so I can put down VO, the initial velocity, is 0. It has to reach a final speed of 100 meters per second for takeoff. I'm going to put these without units now, just to make it simpler. As long as you have units on the final answer, that's all that matters. The distance the plane covers on the runway is 1 kilometer, which is 1,000 meters. And you're looking for the acceleration. So A is your question mark, and you see from this list that T, time, is the missing variable. So if you go to your list of the kinematics equations, the last one on the list, which is v squared equals VO squared plus 2a delta x, is the equation that's missing the T. Now you have to do 3 things in order once you pick the equation. First thing is, if there are any zeros, cross them out of the equation. And we know that VO equals 0, so I'll get rid of that from the equation. So we're now left with v squared equals 2a delta x. Next step is to rearrange the equation before plugging in the variables. So we're trying to get the a by itself. So in this equation, to get the a by itself, we're going to divide both sides by 2 delta x. So the 2's and the delta x's cancel out. So we now have the equation a is equal to v squared over 2 delta x. Now that you have the equation rearranged, this is the part where you plug the numbers in. So the v, we said, was 100, and the delta x was the 1,000. So we get 100 squared divided by 2 times 1,000. That ends up being 10,000 over 2,000, which is equal to 5. And because this is the final answer, we want to have units on this, and acceleration is measured in units of meters per second squared. So now let's do some proportional reasoning. Suppose the plane were to accelerate at double the rate of acceleration found in part A. So the acceleration is twice as much. We still have the same initial speed of 0, and we still have the same distance as 1,000 meters, and we want to find the final speed now at the end of the runway. So because all the variables are exactly the same, the initial speed, the final speed, the distance, and the acceleration, in terms of the stuff we know or what we're looking for, we're going to end up using the same equation. So we'll write this as, just start off with the equation, v squared equals, and I'll go ahead and leave out that VO squared since we know that's 0. So v squared is equal to 2a delta x. Now with proportional reasoning, instead of plugging the numbers in, what you do is you just rearrange the equation for the variable you're looking for, which in this case is v, because it wants the plane's speed at the end of the runway, wants the final speed. So to get v by itself, all we have to do is take the square root of both sides of this equation. So v is equal to square root of 2a delta x. And now this is where the proportional reasoning comes in. It says that the acceleration was double the rate of acceleration found in part A. So we want to make the a 2 times as much. So we're going to multiply this a by a 2. And we're going to see how this side of the equation changed to get this side to change by the same amount. This 2 right here is already part of the equation. This is not how much the equation changed by. The equation changed just by including this extra 2 multiplied by this a, and notice that this a is under a square root sign. So we're multiplying the equation by a 2 under a square root sign, which means that we would do the same thing to the other side of the equation. We're going to multiply it by a 2 that is under a square root sign. And what this is saying is that the final velocity, which originally was 100 meters per second, is now going to be multiplied by the square root of 2. So it will be 100 multiplied by the square root of 2 for that final velocity. And you can leave it in that form if it wants an exact answer, or you can plug this into your calculator and get a decimal answer of 141.21 meters per second. Okay, let's do proportional reasoning on part C. Determine the distance the plane would cover before reaching its required takeoff speed. Well, notice we still don't know anything about the time, so it's still the same 4 variables we're looking at. The initial speed is 0. We want to solve for the delta x this time. It wants the distance covered. The takeoff speed is 100, so we're back to v being equal to 100, and the acceleration is still going to be twice as much. So taking that same equation, which we're starting off as v squared equals 2a delta x, let's rearrange that equation this time to get the delta x by itself. So delta x is equal to v squared over 2a. So now let's do the proportional reasoning. What are we changing this equation by, and how does it affect the delta x? Well, the only thing that was changed was the acceleration. The acceleration was multiplied by a 2. So if we include a 2 multiplied onto this acceleration, remember we're not focusing on this 2 right here because this 2 is part of the original equation. We're only looking at how the equation actually changed. So we multiplied this side of the equation by a 2, but that 2 is in the denominator. So we have to do the same thing on the other side. We have to multiply this side of the equation by a 2 in the denominator, which is the equivalent of multiplying by 1/2. And what this is now telling us is that the distance covered is going to be 1/2 of the original distance covered, and the original distance covered was 1,000 meters. So half of 1,000 meters will give you a delta x of 500 meters. Okay, next part of the problem is a little bit different. Upon taking off, the plane begins ascending at a constant velocity of 100 meters per second at an angle of 20 degrees above the horizontal. So it says it is a constant velocity, which means we're not going to be dealing with the kinematics equations anymore. The only equation we ever use for constant velocity is the v equals delta x over t. So let's draw a diagram of this and figure out how this works. So the plane is ascending at a velocity. So I'm going to draw an arrow to represent the velocity. So the v is equal to 100 meters per second. And because it is ascending at an angle of 20 degrees, theta equals 20 degrees, with respect to the horizontal, so I'll draw a dotted line for the horizontal and a dotted line for the vertical. Part D says, calculate the time it takes from takeoff for the plane to reach its cruising height of 2,000 meters. So we want to figure out how long it takes the plane to go upward by 2,000 meters, which means we actually don't care about the horizontal part of this motion. We only care about the vertical part of this motion. So because velocity is a vector, it can be broken into components, just like a force on a free body diagram can be broken into components. So we can take the horizontal component right here and say that is v times the cosine of theta, and the vertical component, going up this way, is the v times the sine of theta. We're going to call this, the horizontal component is going to be vx, and the vertical component is going to be vy. So vy, which we said is v sine theta, the v was 100 times the sine of the angle, which is 20. So the Vy is equal to 100 sine of 20, which is about 34.2 meters per second. So we're going to be using the Vy in this equation in place of that V because we're only caring about the upward motion. And instead of using a delta x right here, we're going to actually change this to a delta y because delta x implies horizontal motion and delta y implies vertical motion. So we're going to take that equation for constant velocity and rearrange it to get the t by itself. So with t by itself, we have t is equal to delta y over Vy. The delta y was the height that it reaches, which is 2,000, and the Vy is what we just calculated as 34.2, and 2,000 divided by 34.2 gives you a final answer of 58.48 seconds. Part E. If the plane doubled its angle of ascension from 20 degrees to 40 degrees, would the plane reach its 2,000 meter cruising height in exactly half the time calculated in Part D? Well, if you look at how the angle affects things, the angle is part of the sine function, and the trig functions are not linear functions. So if it was a linear function, if that doubled, then it probably would go up to half the time. But since this is not a linear function, it's not going to double it. It will make it go up quicker because it's ascending at a faster vertical rate because the angle is bigger, but it's not going to be exactly half as much. So the answer is no, and you can put the justification because the trigonometric functions sine, cosine, and tangent are not linear functions. Last part is to draw a free body diagram using some forces that you have not seen before, just based on some descriptions. So during the plane's ascent, it experiences 4 forces, and the 3 that haven't been discussed so far are lift, thrust, and drag. So let's go ahead and put the force down that we do know, which is the force that acts on everything on Earth, or near Earth, the gravitational force. So I'll put the downward arrow, label that one as Fg. Now it says the lift force is a force that is perpendicular to the plane's wings that occur due to their shape. So if you think of the plane as kind of moving in this direction during the ascent, going this way, the perpendicular force of lift would actually be going up in this direction, sort of like the normal force for an object on a tilted surface. So we'll add in that arrow, upward an angle, and call that FL for the lift force. Then it says thrust is the forward force of the plane. It's in the direction of motion. So I'll put an arrow going up this way. We're not going to use FT since that's used for tension, so I'll just call this FTH for thrust. And finally, the drag force is the force of air resistance in the opposite direction of motion. So that is going to be going in the opposite direction of the thrust force, and we'll call that one F sub D, the drag force. So one of the forces, the gravitational force, lines up with the XY axis if it's not rotated, and then 3 of the forces, the thrust, the lift, and the drag, line up with the X and Y axis if it is rotated.